You played Vampire Survivors, loved it, and now you want to make your own because you can make it better. You booted up Unity, spawned 10,000 enemies, okay, it's looking good, this is easy. Well, you don't want all the enemies to overlap with each other, so what is the most cost-effective collider you can use? The 2D circle one, of course. Alright, let's slap a circle collider to each enemy, and... bruh. Okay, well, everything in a Survivor's like is about collisions, or simply stuff being aware of being near other stuff. Enemies shouldn't overlap, bullets should hit enemies should hit the player. So then what's the solution for this if we can't use colliders? Don't worry, I got you. In the next 5 minutes or so, you will learn how to handle the physics and updating the logic of 10,000 enemies and 5,000 bullets at once while keeping a high stable FPS. And this solution has no compromises or tricks. We are not going to despawn enemies that you don't see on the screen and magically recycle them on the other edge like some other games do. Vampire Survivors. Whether you want your enemy to walk towards the player or a bullet to check if it's in collision, this will all happen in our update logic for that specific unit. These will be mathematical calculations that we must perform at certain intervals. But obviously, if 10,000 enemies check, if they're close enough to the other 9,999 enemies 50 times per second, you will melt your CPU. So the whole deal is to use smart tricks to make the feeling of that happening without actually doing it, so it's actually possible. In our battle to save your CPU from melting, we will have two main focus points. How often do we calculate and what do we calculate? So let's focus on the what first. You don't need to compare the position of an enemy or a bullet with every other enemy. An enemy all the way over here can't possibly be in collision with an enemy over here. So our saving grace is called spatial partitioning. Sounds fancy, but it's basically dividing the field into partitions where the units will check, hey, are we in contact only if they're in the same partition. Every time a unit is spawned, we use this function to map their actual position into a partition. This will depend on the size of your map or how many partitions you have. For example, my map is 100 units tall and 100 units wide, and it has 10,000 partitions. So each partition is just a 1x1 square. And this is how I calculate the spatial groups for a hard-coded width, height, and partition size values. Since my map size never changes, I don't need to recalculate them every time. But if you're a freak, here's the code that will work for any amount of partitions, height, and width. Every time the enemy moves, it will check if it moved into a different spatial partition and update accordingly. When each enemy is asking, hey, am I in collision? It will only calculate this for the other enemies in the same partition, which will be a very small group. And I know what you're thinking, hey, what if the enemy is right here on the edge of the next partition? Or what if my unit is larger than the whole size of a partition itself? Well, that's easy. In that case, we will just grab the surrounding partitions, as many as we need to, and then run our calculations for all the enemies together in that group of partitions. Here's what that looks like. First, we need a function to get all the surrounding spatial groups. You don't need to understand the math here. To be honest, neither do I, but I tested it and it works. Intuitively, if I ask you, what are the surrounding partitions of this group, you know I want these ones. Or, if I want the surrounding partitions with a radius of 2 over here, you know I want those ones. So once you have the surrounding collection of partitions, you can simply get all the enemies that exist in all those partitions together. Then, the rest of the logic is the same. Here's a list of enemies and calculate whatever you want. It is time to discuss the other part, the how often we calculate. Let's look at the simple case first, the update logic of the bullets. Because it runs every frame, we can do it right here on the bullet script's fixed update. By default, the fixed update runs 50 frames per second in Unity unless you change it. So on this update logic, we update the position. For the collision, first we get the bullet's spatial group. If the spatial group has changed, we get the surrounding spatial groups. Then we can check if we are close enough to the other enemies that are currently in those spatial groups. So this was the case for updating every frame. Now let's look at the enemies logic where I only want to update once a second. You might think, let's just have a timer and once it hits 50, update all the enemies. Well then, you will have 10,000 enemies all calculating a dozen different things, which will cause a lag spike. So it's a much better approach to cut this logic up into smaller pieces and run them piece by piece. To achieve this, I created 50 groups of enemies and I called the update logic function for the particular group each frame. And this is pretty much it. It is simple and it works. Except what happens if enemies die or new ones spawn? You can just spawn them in and randomly place them in a batch and you will have about equal enemies in each batch, but that's not guaranteed, and I want to make sure that there are equal number of enemies in each batch as new ones spawn and die. I'm sure there are other ways to do this, but here's how I did it. I used two different data structures. First one is a batch score, which will simply hold a score for each batch, and you may have noticed the iComparable interface and the compare to function here. All this does is tell the code how to compare two batch scores if that happens. So it's a no-brainer to just say that, hey, just, whoever has the best score is the better option. But what if the two batches have equal scores? In that case, I never want two batches to be truly equal, because we still need to make a decision as to which batch the enemy belongs to. So in that case, I just tell the function to compare them by their batch IDs. Since their IDs are unique, they won't ever be equal. Now that we have a whole set of batches and their scores, only thing left to do is to quickly know which batch has the best score. And for that we need a sorted set. If you aren't sure why this is necessary, let's go through a working example, one with a list and one with a sorted set. In the case of a list, we just update the score of our batch when the enemy dies, but every time we want to spawn an enemy, we need to check every batch for their score to find the best one. So assuming equal number of enemies die and spawn, each cycle will be 51 operations. What about the case for the sorted set? Now every time an enemy dies, we just update their score and then resort the sorted set. On the other hand, when a new enemy spawns, because the set is sorted, we just grab the best score and then resort the batches. So in total, it will cost us 2 plus 2 log n operations. So if there are 50 batches, there will be about 6, which is much better than 51 operations. To show this implementation on action, when I spawn an enemy, I call getBestBatch, which gets me the ID and then resorts the batches. And similarly, when an enemy dies, I just call updateBatch, which updates the scores of the specific batch and resorts all the batches again. I hope you found this video helpful. Now go ahead and make your own crazy survivors like, but do share what your game will be about down below. Thanks for watching. See you next time.